Welcome to today's tutorial on derived units and percent air. We have two essential questions. First one is, how are some important derived units used in chemistry? Second is, how do we determine the accuracy of measurements in the lab? Derived units are a unit that results from a mathematical combination of units. We've been using derived units for most of our scholastic career. We know that area is the length times the width. And when we measure in length and width, we usually measure in meters or centimeters. And so when we multiply those two units together, we get the derived unit of meters squared. Same is true with volume. We measure length times width times height in meters. And when we multiply those three measurements together, we get the derived unit of meters cubed. Two important ones that we use are density and concentration when we're talking about chemistry. Density is the mass of a substance divided by its volume. We measure mass in grams, and we measure volume in milliliters. And so we have a derived unit for density of grams per milliliter. The same is true with concentration. We measure the amount of a substance divided by its volume. When we measure amount of a substance, we measure in moles. When we measure volume, we can measure in milliliters or liters, and so our derived unit becomes moles per liter. When we're using dimensional analysis with derived units, it requires very special care. When we have 1 cubic meter and we want to know how many cubic centimeters are there, we have to be careful. Sorry about that. Go back here and grab my pen. When we have 1 meter cubed over 1 and we do our dimensional analysis, we know that there's 100 centimeters in every 1 meter. But this meter here is to the first, and so that only cancels out one of these 3 meters. And so we would have to do this 3 times in order to get rid of the cubic meters. So these 3 meters would then cancel out cubic meters, and I would have centimeters times centimeters times centimeters equaling cubic centimeters. And we have 1, 2, 3, 4, 5, 6, so we have 1 times 10 to the 6th cubic centimeters. So we have to be very careful when using derived units in our dimensional analysis. So let's do one more example. We have 3.6 times 10 to the 8th as our given, and that's in cubic millimeters. And we want to know how many milliliters. So I know that I have to set up my truths, millimeters to centimeters, centimeters, and then I know cubic centimeters to milliliters. And so there's 1 centimeter in every 10 millimeters, and I'm just going to go ahead and cube that. And then I know there's 1 cubic centimeter in 1 milliliter. When I do this problem, since I have 10 times 10 times 10, or 3 tens here, so minus 8 minus 3 is 5, so 3.6 times 10 to the 5th milliliters. So that's derived unit conversions, and I said one of the important ones that we use in chemistry is density, and we see these logs floating along the river here after these trees have been chopped down. And density is an intensive property, meaning that we don't have to know exactly how much. It doesn't depend on how much of a substance we have. This is a physical property of pure substances, so we can use it to identify what a substance is, or we can use density to convert between mass and volume. So density is mass over volume, or D equals M over V. And I've given you a few densities of pure substances. And one that we're going to use today is aluminum, 2.70 grams per milliliter. So let's do a couple of example problems. The first one is with zinc metal. When we do these problems, I'd like you to do them a certain way. I want you to first write down your knowns. So for this problem, 18.2 grams sample of zinc metal has a volume of 2.55 cubic centimeters. What is the density? Well, I don't know my density. That's what I'm going to be solving for. My mass is 18.2 grams, and my volume is 2.55 cubic centimeters. Next, I'm going to write my equation. So my equation for density is D equals M over V. I'm solving for density, which is what I'm solving for in my equation here. So now I can just plug in my numbers and calculate, or plug and chug. So I've got 18.2 grams divided by 2.55 cubic centimeters, and when I do that math, I get 7.13725, and I believe it keeps repeating if you've done this with me on a calculator, but I've only got 3 sig figs in both of my givens. And so I can only have 3 sig figs in my answers, so I'm going to round to my third sig fig, and when I do that, I get 7.14 grams per cubic centimeter, or grams per milliliter. Let's try another density problem where we're solving for mass. What is the mass of 2.49 cubic centimeters of aluminum? So my first job is to, one, make sure that I write out my knowns. So my density I know for aluminum is 2.70 grams per milliliter. My mass is what I'm looking for, and my volume is 2.49 cubic centimeters, and that's the same thing as milliliters. So my next job is number 2, to write out my equation. D equals M over V. But this time I want to solve for mass. So I'm going to rewrite this, and you should do this too in your problems. M equals D times V. And so now I can plug in my numbers and chug them out. Plug and chug. So I have my density as 2.70 grams per milliliters. Notice I'm using my units, because my units shall set me free. 2.49 milliliters. Milliliters cancels out. I'm left with grams, and that's something that we measure mass in. So when I work out this math on my calculator, I get 6.723 grams. I have 3 sig figs in both of my givens, so I can only have 3 sig figs in my answer, 6.72 grams. So let's write one more step here that I didn't write down on the previous page. Number 4 is use sig figs. Alright, let's do one more where we're looking for the volume. What is the volume of 50 grams of aluminum? So my first thing I have to do is write out my givens. My density is 2.70 grams per milliliter. My mass is 50.0 grams. My volume is what I'm looking for. My next step is to write out my equation. D equals M over V. And I'm going to manipulate my equation. V is going to come over to this side. D is going to come down below, so I have mass over density. When I plug and chug, I've got 50.0 grams over 2.70 grams over milliliters. Grams is going to cancel out. My milliliters, since it's the denominator of a denominator, is going to be able to move up to the numerator. And when I calculate this out, I get 18.5 185 repeating. And I've got 3 sig figs. I got to make sure I use the correct number of sig figs. So my volume is going to equal 18.5 milliliters or cubic centimeters of aluminum. So there's density. Let's talk a little bit more about accuracy and precision. Accuracy, remember, is a measure of how close a measurement is to the correct or accepted value of a quantity being measured. Precision is a measure of how close a series of measurements are to one another. Precise measurements are going to be highly reproducible even if the measurements are not near their accurate or correct value. And you guys have seen these targets before, and so here, since our measurements, which are indicated by the blue darts here, are all close together, they're highly precise and they're close to the middle of our target, which means they're highly accurate. When we do a lab, one of the things we want to do is make sure that we report how accurate our measurements are. One of the ways that we do this is through sig figs. One of the ways that we do that with precision is through sig figs. But the accuracy of a measurement is dependent upon our measurements themselves and how accurate our measuring device is. So percent error is the absolute value of the error divided by the accepted value multiplied by 100. So the accepted value, or the theoretical value, this is also accepted, measures the accuracy of our measurement. So let's do a quick example here. The density of our aluminum is 2.70 grams. This is our accepted value, or our theoretical value. In an experiment, you determine the density of a sample of aluminum to be 2.42 grams. This is our experimental. So what is the percent error? Well, my percent error is going to be the absolute value of our experimental minus the accepted divided by the accepted times 100. I kind of did this out of order, but remember my accepted value is 2.70, my experimental is 2.42. So plug and chug here, 2.422 grams per milliliter minus 2.70 grams per milliliter, and I want the absolute value of that, divided by 2.70 grams per milliliter. Now, since these are being subtracted, remember that grams per milliliter really could be moved outside of these brackets, and so these both are going to be canceled by this one down here. And so when we do this, 2.42 minus 2.70 divided by 2.70 times 100, my percent error is going to equal 10.370370 on and so forth. But remember, I only have 3 sig figs in each of my givens. So my percent error needs to only have 3 sig figs. So there's my answer. Hopefully this video will help you when you're doing problems on density or any derived unit, and then it will also, you can also come back to this if you ever need to know how to do percent error again. All right, have a great night.